the filter function will be splitted in different intervals, and we define the overlap, the percentage of the overlap between these intervals. So this is our filter function. In this case, we consider the simple one, which is the identity. So from the 6 feature, we map them to 6 feature. And then we put the data into overlapping bins using this number of the intervals and the overlapping percentage. And we cluster each bin using dbScan. It could be another clustering algorithm, but in this case, we consider it dbScan, density-based scan, and a distance function. And finally, as I said, we create the graph where we have each vertex is the cluster of a bin, and the edge represents non-empty interaction between clusters. So the clustering part, where we apply this in each interval that we obtain from the filtering function, we basically apply dbScan is a classical one, which needs 2 parameters. The maximum distance between epsilon, which is the maximum distance between 2 points to consider in the same cluster. The minimum points, which is the number of neighbors that the pointer should have to be considered as a cluster. And the used function in our case was 2 metrics. The first one is the difference for timestamp attribute IP destination and source addresses, because the difference makes sense, but it's critical because sometimes when we have 2 IP addresses from 2 ASP, that doesn't make sense. But in this case, since at least for the IP destination address, all these addresses are consecutive, so it works. And for the metric regarding the protocol and port names, we use the equality metric, so 0 or 1. So this is the distance function that we are using for the dbScan. A first example, when we applied this methodology on the darknet traffic, so we extracted a first data set, so it's only scanning activities, one scanning activities and each associated packets, which are extracted manually. We considered only 2 features from the 6, the source IP address and destination IP address, just to motivate and show how it works in darknet traffic. We considered 30 intervals and 50% of overlap between this for the filter function, which is the same. For this case, it maps the 2 first features to the source IP address. So this is the graph represents, or this figure represents the data. So we have the source IP addresses and the destination IP addresses. We observe these vertical lines, which mean that are scanning activities. Usually each source is scanning multiple IP addresses. This is the graph that we obtained using the mapper algorithm with these parameters. And this is the figure where we colored each line with the color of the nodes of the graph. So for example, this one is this one. We observe it is linked to the other one, which is close, because the destination IP address is also close, so the difference is small. This one is the last one, because it is so far regarding the destination, the source IP address from the other, and these 2 nodes are these 2 vertical lines. So this technique, this graph, represents well the scanning activities. This is the goal of this illustration. So then we applied this on this nosy traffic, which is a mix of multiple scanning activities, multiple DDoS activities or others. We make some parameters, so 1,000 packets, with this is the epsilon and the mean points for the dbScan algorithm. The verbal overlap was 10%, and we were able to extract some patterns from this nosy traffic using this graph, which is the output of the mapper. So the large green dot represents the scanning activities against this pore. The red compound represents a probing or scanning of telnet and SSH access. The orange compound is this one, which is per scan, so it's scanning random scan. And the yellow compound, which is this one, represents randomized scans. So from this, we were able to obtain this. And for us, from security analyst, this is very important because we are able to define single patterns, not a mix of packets that we are not able to interpret. Then we applied this on a specific way to only extract scanning activities. So we make these parameters with 8,000 packets. The epsilon, the mean points, the overlap, 5%, and Yes, the question is that how to estimate these parameters. All these parameters are estimated using a trial and error. So we try, we check the pattern, if it's okay. Otherwise, we check another parameter and so on. But if you find these parameters, it remains stable. So it is able to extract always the same patterns. So for this, we are able to extract the scanning activities from all this noisy data. And we compared our result with an EDS, which is Sirikata, which is now an EDS, state of the art. And Sirikata was able to detect only 4 scanning activities from this. Then we applied the same method to the DDoS activities. So same way, we identified some UDP packets from this noisy traffic. We applied the technique with these parameters, and we were also able to identify the DDoS activity and extract this activity from this darknet. Just some points about the performance of this technique. So all these results are with the simple machine. It was a quad-core CPU with 283 gigahertz, with 15 gigabytes of RAM, with the Linux. The mapping of 1024 packets takes between half of a second and 1 second. To analyze the 3 million of packets, which is 1 day, 11 minutes. And for example, if we take a window which represents something like 32,768 packets, which represents a half of 15 minutes, we are able to analyze them in 2 minutes. So for example, we can target an attacker or known source, and we can extract all the features of this attacker in 2 minutes, which is interesting mainly for security analysts. So we can increase the performance of this algorithm by using more computing power. Here we are using simple machine, traditional one, classical one, and also to parallelize this tool to make some parallelization of the clustering of the feature extraction and the computation of the filtering function to make near real-time analysis. So some work could be done to enhance the performance of this technique. So the conclusion of this work, so we basically used a well-known technique, which is DDA, and more specifically the mapper algorithm from this technique. And we apply this technique to darknet traffic. The goal is to extract some useful patterns, mainly DDoS patterns, scanning patterns that could be used in second step by a security analyst or to build the CM, for example, which is presented by Gabriel. So we can put this type of activities and their models in the CM to detect more activities. The algorithm is using a filter function with a partial clustering. It could be DBScan or other one, but for us it was DBScan provided the best results. And the experimental results, we were able to discover more patterns than a well-known IDS, which was Sirikata. So as a future work, including more packet features, because here we only considered 6 features, so we need more, and we can extract this from the packets that we are of the darknet, and extract more activities and analyze their persistences. And this is an important point because for now we are able to observe only over a time window or a space window. And the idea is to find how this activity will persist over space and over time. So this could be useful to identify more persistent activities, which is in relation with advanced persistent threats. So thank you very much for your attention. And if you have a question, I'm welcome. I will answer. Thank you very much.
Thank you. You definitely make the darknet look much brighter and more colorful with this presentation than what the name makes us expect. Okay. So, are there any questions? Yes.
Thank you for your presentation. My question is, you have used IP addresses for the visualization of the source and destination. But what happens if you include a lot of different many features, like, for example, ports, features like TTL, or other things?
Yes.
Is the visualization so clear, or?
Yes, I mean, this is because we are doing a 3D visualization. So for this reason, we selected only the IP address and the source, for example, and the destination IP address and the destination port. But what we are, the most important in this graph, this is what we need. Because this is the graph, which is the output of the mapper, and it is the compressed representation of the feature that we are selected. But this or the other one, this is only a kind of visualization, so we can modify this by the TTL. It could be something else. But since it is in 3D, so we need only 3 dimensions for the visualization. But I mean, this could be adapted. We can use other features to visualize the output of the mapper using other properties, not only the IP address or the ports. So it could be easily modified.
Thank you.
Do we have more questions?
Hello, thank you very much for the presentation. So regarding the telnet and SSH probing attacks, I guess you infer those by the destination ports, right? Because you don't have, you're passive detection, okay. And another thing is, have you detected scanning activities that are known? Because, for example, University of Michigan launches ZMAP and Shodan, I mean, you have the option to do that, so.
Yeah. Yes, thank you for the question. Yes, yes. Some of them are from Michigan, from ZMAP. So we can check this with the IP source, the source address, by making some DNS, using the DNS. So we see that it was from the University of Michigan. Also, we observed some patterns from Sudan. In the same case, we used the sources. We inspected the source and we find that they are from Sudan. Yes, with this, yes, we were able to detect known scanning activities from known sources like Michigan or Sudan. There is also from, maybe there is the University of Berkeley, they did some scanning also. Yes, but also we are able to extract more. So we found unknown sources. It could be botnets. It could be, we observed some patterns when we have this day in the internet where DIN, it was attacked by a botnet, the big botnet, and we observed some patterns, yes. We were able to observe some patterns of scanning from many machines. So, I mean, it's infected machines. So, yes, good question. Yeah.
Okay. So, in the interest of time, I would propose to take the next questions in the break and directly contact the speakers during the break now. Thank you very much to all the 3 speakers and to you attending this session.
So, we can take a short break, 5 minutes. In the meantime, so we have the certificate of attendance laid out in the desk, the registration desk. So if you need it, please grab it. And in 5 minutes, please grab a cup of coffee and then we just can continue from there.
a total of 3 presentations. 2 are about phylogeny, video phylogeny and image phylogeny, and the other is instead about content identification fast. Okay, let's start with the first talk by Stefano Tubaro, which is on hash-based frame selection for video phylogeny.
Thank you. And how does this work here? The first one. First of all, thank you to all of you to be here in this last session of this conference. And the title of this presentation is Hash-Based Frame Selection for Video Phylogeny, and it is a joint work of my group at the Politecnico di Milano and the group of Professor Rocha at the University of Campinas in Brazil. And it is part of the Media Forensic Integrity Analysis project that has been financed by the DARPA project that has been presented by David yesterday, 2 days ago. As you know, currently a large part of the users that use the social network and the sharing platforms are sharing not only images but also videos. And moreover, the same video content can be several times edited and republished, creating what is called a group of near duplicated objects or near duplicated video. And there are a relationship between the objects that are in this block of near duplicated objects, in the sense that there is a father of all the objects, the original content from which all the other video has been created, and a series of connections that illustrates the history, the evolution of the object from its origin to create the entire set of videos that constitute this group of near duplicated videos. And the structure that describes this history, this is evolution, is normally called the phylogeny tree that describes the objects. And obviously, when this tree is known, it is possible to know what is the object that has been used to create all the other videos in the group of near duplicated objects, and also to understand how this object is changed in the time in order to create all the objects in the set that we consider. And obviously, in the literature, there are several contributions regarding the creation of phylogeny tree for images. While for videos, the contribution present in the literature is very limited. And we have carried out some work in this direction in order to be able to create phylogeny tree also for videos. And as for images, the first step in the creation of this tree is the estimation of some dissimilarity score between each pair of objects that are present in the set of near duplicated objects. And what is the typical way in which a dissimilarity measure can be obtained between a couple of videos? We consider the first, the 2 videos taken among all the that are present in the group that we are considering. And at first we have to align in the temporal direction the two videos. And this operation obviously is essential to obtain significant results evaluating these dissimilarities. And moreover, to reduce the computational load of the entire process, after that the two videos has been aligned, we select some significant keyframe that are used for the evaluation of the dissimilarity. After the alignment and the keyframe selection, the steps for evaluating the dissimilarity are essentially oriented to modify one of the two objects in order that the similarity between one of the two original objects and the other that has been modified is as similar as much as possible, in order to take into account that during the processing of the object, they must be geometrically modified, or the color can be modified, and obviously the coding parameter of the object can be modified during the editing process. And therefore, we have a pipeline of three steps in which at first one of the two objects, in this case the object named K2, is geometrically registered on the other one, considering the keyframes that has been obtained. And this is the step exactly similar to what done in the case of evaluating the dissimilarity between a couple of simple images. And the process involves the extraction of feature point and the matching of feature points, and then the creation of an affine transformation that modify in the best possible way one image to the other. The second step is a color transformation in order to create the best possible matches between the histogram of the two keyframes that has been considered. And the last step is the recording of the one of the two videos using the same coding parameters of the other videos. And in particular, due to the fact that we are considering only some keyframes, we record only these keyframes, and on the reference video, that is in this case the videos indicated by K1, we consider only keyframes that are intra-coded. Therefore, frames that are coded without referring to other frames in the sequence. And this allows a reduction of the computational load. That is an important thing that must be taken into account in this operation, and also create a system that is robust against frame drops. And therefore, the recording process that are here indicated in the box, in the highlighted box, is carried out using only intra-frame approach, because the other reference frames in the other video is encoded with an intermode. In any case, the step after this transformation of the keyframes of one video on the keyframes of the other videos is the evaluation of the mean square error between each of these keyframes. And the results of this mean square error is directly an indication of the dissimilarity between the two videos that we are considering. And low dissimilarity indicate that a parentship of the type parent-child is in some way highly probable, while a high dissimilarity indicates that a relationship of the type father-son is is not probable in the creation of the content. And just after the evaluation of all the possible dissimilarities that are calculated in both the direction, therefore from video K1 toward video K2 and vice versa, then considering the entire pool of possible dissimilarities, using standard algorithm like the oriented Kruskal algorithm or the optimal branching algorithm, it is possible to create the phylogeny tree. I just want to spend a few words regarding the time alignment of the two sequences and the frame selection that I mentioned at the beginning of my presentation. The idea here is to take into account two situations that in some way are quite common in the editing of a video object. That is some changes in the frame rate of the videos and also some frame drops from the frame deletion in one video to create the other. And these two types of editing are not considered in the contribution currently present in the literature. And the first step is the evaluation of binary hashes from each frames of the objects using some standard techniques. And after this, it is possible to evaluate a distance between the hashes that represents couple of frames belonging to the two sequence, and it is possible to obtain a scheme like the one that is reported in the right of the slide, in which low values of distance indicates that the two frames are very similar one to the other, while high values indicate that the two frames are not similar one to the other. And when this structure is known, it is easily possible to identify segments that represents sets of frames that corresponds on the two videos. And here it is indicated two of these segments. And it is possible to also to associate some confidence to each segment, considering how deep are the minimum that are present on each line that are present in the scheme, in each segment that are present in the scheme. And therefore, on each readable segment that we are able to identify on this structure, it is possible to identify the keyframe that I have mentioned at the beginning of my presentation. And moreover, we select keyframes, I said before, that on one of the two sequences has been coded in intermode in order to be able to recode the other keyframes in the intermode also. And obviously, using this approach, it is clearly possible to manage the fact that some frame drops has been introduced on the sequence, in the sense that when a frame drops is introduced on one of the two sequences that we consider, we have a structure like the one that I have indicated here, in which the ellipse clearly indicates that some frames are missed in one of the two sequences. And also we can easily take into account a change in the frame rate of one sequence with respect to the other, in the sense that the segment that we identify will not have a slope of 45 degrees, but a different slope. And after all this process, we have taken a series of experiments, creating a data set of video phylogeny trees. In particular, we have created 250 different phylogeny trees and therefore 250 set of near duplicated objects. Each set of duplicated objects is composed by 10 elements, therefore 10 nodes. And we have considered part of this data set that includes also frame rates and frame drops, and another set that is not containing frame drops and frame rate changes. And as far as the evaluation of the performance of the algorithm, we have used the typical metrics that are used in the evaluation of the phylogeny trees, that is the mean number of correct roots that has been indicated, the mean number of correct edges, therefore the correct father-son relationship that has been obtained, the number of final leaves, of correct final leaves that has been obtained for the phylogeny trees that has been obtained, and also the mean correct number of ancestries relationships. Therefore, we also considering relationships like grandfather-son type. And it is quite obvious that if you consider a data set in which there are not present frame changes and frame drops, the performance of the proposed technique is quite similar to what is currently proposed in the literature. While if you considering also frame drops and frame changes in the sequence that belong to the considered data set, the performance of the proposed techniques are significantly better than the performance of the standard techniques that is present in the literature. I think that this simply summarizes what I said before. And if you want to find more information on the project that I mentioned at the beginning of my presentation, here is the indication where you can find more information. And thank you again to David and DARPA to have financed our activities.
Okay, we are in time, so there is the time for some questions.
Thank you. Just to give everybody, sort of a bigger picture there. So you're calling it a tree, right? But I think, and you started at the end to use the term frame changes. Were you still referring to frame rates there?
Yeah.
Okay. Okay.
Excuse me.
Well, because that's kind of important because you're considering changes to one video, right? Have you thought about what happens when you take a bunch of videos and put them together to make a new one? Because then it's not really a tree anymore, right? It's a graph?
Yeah, this is in some way, can I say, a more complex problem in the sense that at this moment we have considered what we call the user-generated content, in which normally not so complex editing operation as performed, in the sense that normally not different videos are fused together. But for sure, if we also consider this case, the problems becomes more and more complex, and we don't consider only simple trees, but we have to consider a graph, and in general, very complex structure that describes the relationships between all the objects that belong to the same set of near duplicated objects.
Okay, yeah, so I'll just, I'll give you a hint that,
For sure, we are at the beginning of considering the project.
And to tell the rest of the community also, the data that's being created will have donor, basically what we call donor videos or images, and objects will be able to be put into the scene. So like you might have a car that gets put into a scene from another video. Those kinds of relationships are definitely of interest. So it'll be interesting to see how the hashing functions work for that. So.
On one, hash is quite a robust approach in the sense that for sure in a very large of cases it is able to synchronize one video with another video that contain a significant part of the scene, in the sense something like 50–60% of the scene. In this case, I am quite sure that the hash is able to work correctly. But for sure, if a video is composed by using an object or a background coming from a video and another object used as foreground, probably the synchronization with respect to the background could be addressed by using this, in some way, simple and fast approach based on hashes. The synchronization of the foreground object that is obtained from another video could be more complex.
Okay. Any other questions? I have just a question on the data. Which is the resolution of the video you used in your data set?
At this moment, we have used standard resolution videos, therefore are 500 by 700 pixels about.
So they are all the videos are all the same resolution in your data set?
It is not strictly necessary because the geometrical the step of geometrical registration can take into account also that the videos can have different space resolution.
Okay. Thank you to the speaker, but he has to stay there.
Just a second.
Because there is the second presentation. So let's, however, thank the speaker. And let's start to the second presentation, which is about image phylogeny, particularly about phylogenetic analysis of near duplicate and semantically similar images using viewpoint localization.
I am not so familiar with this PC. May I have some problem, but it seems that it works. Okay. Also, this work is a result of the activity of our group, of my group at the Politecnico di Milano, and it is part of the same project that I mentioned before. In this case, as Luisa said, the problem that we are considering is relative to images and not to videos, and start from the idea that considering a particular place or a particular event and the images that are uploaded, for example, on some sharing platform relative to this event and or this place, can be subdivided in some way in two types. On one type of images are images that are relative to the same scene, but are taken by different users or in any case by slightly or largely different viewpoints. Therefore, there are images that are semantically similar one to the other, but they are not near duplicated one to the other. At the same time, in the same pool of images relative to the same event, to the same place, can be present also images that are an editing of other images that are still present in the pool. And in this case, we can think to block of images that are really near duplicated objects. And therefore, if we want to describe the more simple relationship between this object, considering that there are no can I say, there is not present the fact that one image is obtained and mixed together more than one of the other images. In this case, in any case, if the problem that we are considering is very simple, the use of a unique phylogeny tree to describe all the set of viable images is not enough. It is necessary to use what is called a phylogeny forest, in the sense that each subblock of images that can be considered as near duplicated objects must be described by a different phylogeny tree. And this, the ensemble of all the phylogeny trees that we have will constitute the phylogeny forest that describes the entire set of images that we have. And what is present in the literature regarding this type of problems? At this moment, there are some contributions from the groups of Professor Roca, in which all the images are considered together. At first, a single bit tree is constituted, and then this tree is split in different subtrees in order to create this forest. The main problem of this approach is that it is necessary to evaluate the dissimilarities between all the possible couples of images present in the set that we have. Therefore, if we have n images in the entire set, the number of dissimilarity that must be evaluated is near to n squared. Our approach is in some way different, in the sense that we want to apply some preprocessing to the set of images that we have in order to identify, as best as possible, obviously, images that are taken from the same viewpoint. And these images taken by the same viewpoints, they constitute for sure a block of near duplicated objects. And therefore, we apply this preprocessing in order to split directly the entire set of images in blocks of sub-blocks of images that are, in our idea, blocks of near duplicated objects. And then we can apply standard techniques for evaluating the phylogeny tree for each subblock. And the idea of estimating what images are taken from the same viewpoints is based on the creation of a 3D model of the scene, and then the mapping of each images on this 3D model in order to see what images can be considered acquired by the same viewpoint. In some situation, a 3D model can exist in any case, and obviously in this case it can be possible to use. Otherwise, by using some photogrammetric approach or a computer vision approach, it is possible to realize this set of 3D points that represent how detectable feature points in the images can be projected in the 3D space. And for this purpose, some standard techniques like bundle adjustment approach can be used. When it is the set of 3D points that represents the feature point that has been matched between images has been reprojected in the space, it is also possible to reconstruct the 3D position and the orientation of the camera that has been taken each of the images that has been considered in the pool. And we rely essentially on the translational vector that describe the position of the camera that has acquired each of the images that we have considered. And then our second step is to try to merge together images that has been characterized by similar translational vector. And to this purpose, we have using a k-means approach, using considering at first a number of clusters that are significantly larger with respect to what we normally expect, and to assign after this first step of the k-means selection an uncertainty to each cluster that is based on the number of common matched key points that are present on the images belong to each element or each cluster that we are considering. And then we have a merging step that tries to put together as much as possible the number of clusters that has been obtained in the first step of the process in order to reduce the number of clusters and to obtain the correct number of clusters that represent sets of images that has been taken from the same viewpoint. And then the steps are quite similar to what I have presented in my previous presentation, in the sense that the dissimilarity between each pair of images belonging to the same cluster is evaluated, and then on the basis of this evaluated dissimilarities is possible to reconstruct the phylogeny tree that describe each subblock of images that we have. Just something about the results. We have considered 3 different scenes in our experiment, and for each scene we have considered an increasing number of different viewpoints, from 10 to 16, and from each viewpoint we have generated a set of near duplicated objects in which each set have a number of images that varies from 7 to 20. And as evaluation metrics, we have used, in this case, 6 different evaluation metrics. The first 4 are the same that I tried to describe in my previous description, and are the 4 metrics that are normally used to analyze the quality of the quality associated to the generation of a phylogeny tree. And the last 2 metrics are, one, the percentage of correctly reconstructed cluster, and with respect to the ground truth that we have, and the last parameter, or the last metric, is the percentage of saved number of image comparison with respect to those that are made by the standard approach, that are something very similar to n square, where n is the total number of images that we are considering. And here is presented some results in which there are 5 curves. The first 2 is relative to the percentage of correct cluster that has been detected by the standard approach and the approach that we have proposed when the number of different viewpoints that are present increases from 3 to 8. And it is easy to see that this mean number of correct cluster decreases for the state-of-the-art approach when the number of considered viewpoint is increasing. It is in some way quite normal because the approach starts from creating at first a unique tree and then try to split it in a series of different trees, while in our approach we try to obtain directly the final results by using some preprocessing as I described. And in fact, in our approach, the number of correct cluster is extremely similar to the 100%. And the other 2 curves that are presented here is relative to the mean correct number of roots that has been detected by the standard approach and the approach that we propose. And also in this case, it is possible to see that the number of correct roots decreases when the number of viewpoints increases for the state-of-the-art approach, while we maintain about the 80% of current detected roots for all the possible number of viewpoints that we are considering. And also considering the percentage of number of reduced distances or dissimilarities that are calculated with the standard approach, it is easy to see that we are always over the 90% less comparison or less dissimilarity with respect to the standard approach. And also for the other metrics that we have considered, we are about the same results, in the sense that our approach outperforms in all the situations the standard approach. Just to conclude, we have presented a technique for phylogeny forest creation when the block of images that we are considering includes both semantically similar and near duplicated objects, and it is based on a preprocessing in which the images are separated in cluster by using 3D information that can be obtained directly by the image itself, and then on each cluster standard technique for a phylogeny tree is used. And in any case, we have a significant gain in the computational load with respect to the state-of-the-art approach present in the literature. Okay.
Okay, thanks.
I tried to summarize as much as possible,
perfectly in time.
because I imagine that
yes, we are
all
in
of
time.
us want to conclude.
Okay, are there some questions? Yes.
It seems that the first step, I mean, the matching to the 3D scene seems a little complicated, and for more complicated scenes, it might be a problem. I mean, in this case, you had buildings, relatively well-defined structures, and when you have some more complicated scenes, like maybe a crowd or maybe something like this, then maybe this approach is not the best. And I was thinking, there are some techniques based on visual descriptors like MPEG-7 descriptors or visual hashes or things like this. And would you say that maybe would it be possible to exchange this step for something like this?
I think that it depends to the type of the scene, and
Yes.
generally, I don't know completely the MPEG-7 descriptors, but from what I know, they are not specifically designed to separate images that are taken from not so different point of view, because they are generally oriented to give a general description of the scene. But in any case, I agree completely with you that in some way, simple situation like the ones that we are considering, the approach is working. In some way, it is a little bit complicated because this creation of the 3D set of points requires a certain amount of computational load. Currently, not so much with respect to the available power that is normally available on a PC, but in any case, a significant amount. And for sure, this type of description can be complemented with other type of local or general descriptor in order to increase the capability of discriminating the correct way between semantically similar objects and near duplicated objects. Therefore, I think that this could be only a first step to create something that works in this preprocessing. But probably not probably, for sure, this preprocess must be increased, including other descriptor, other type of describe the images in order to increase its capability to separate near duplicate objects and semantically similar objects.
Okay, thank you.
Any other questions?
So the purpose of getting this 3D reconstruction is mostly like getting the real world camera coordinates, or is it totally
I don't
different?
understand, excuse me.
So you have a 3D model, right, for 3D reconstruction. So the objective of it is to obtain the real world camera coordinates, or it's totally different, something different?
Yeah. When the process that through which it is possible to obtain the 3D position of the points also give us the position of the cameras in some coordinate system. That is a coordinate system that depends to some scale that is not known, but for our purposes, it's not important to know the correct position of the cameras, but in some known reference frame, but also to know if there are some difference between the position of the camera that has acquired one image and the other, in order to have something on which some clustering algorithm can work to separate the images.
So these coordinates are estimated, or?
Yeah,
They are estimated. Okay, yeah. Thank you.
Okay, thank you again to Stefano. Okay, we can pass to the last presentation. The presentation is about the fast content identification in high-dimensional feature spaces using sparse ternary codes. And it will be presented by Sorab Ferdowski.
So thank you very much. I'm happy to be the last presenter of this conference. So the topic is about basically search, fast search in high-dimensional and large-scale databases. So after an introduction and formulation, I will very briefly talk about what is happening in the state of the art and the method we propose called sparse ternary codes from two viewpoints, a probabilistic viewpoint and a signal approximation viewpoint, and experiments and conclusions. So imagine applications like identification of humans based on some biometrics. For example, you have a fingerprint of a bunch of people registered, enrolled in a database, and someone comes and claims an identity to be belonging to this category. Or identification of objects, consumer product packages using physical unclonable functions, or in multimedia, for example, that you're presented a piece of a video and you want to see whether it's infringing the copyright law or not. So the basic idea behind all these applications is that you want to, a query is being introduced and you want to find similar items within that database, and you hope that the semantic similarity is somehow reflected using some feature extraction procedure in neighborhood and distance information. So the problem similarity search will then reduce to simply to nearest neighbor search. And of course, this general problem can have applications in mainly computer vision, also the IFS community, and information retrieval. So basically the schema of the whole system is like this. You are first given capital N items, features are extracted in a database, and a query, which is basically a distorted or noisy version of some of these items, is being presented. And actually the enrollment procedure is never perfect, so we always have this noise. But in this talk, we basically focus only on this search part. We assume that these given features are already good, and let's see what we can do to make this search more efficient. So to formalize the problem, we are given a vector Q in a d-dimensional space, a bunch of feature vectors F in the same vectorial space, and a distance similarity measure. Mainly we're talking about Euclidean distance, and the objective is to find K most similar or items which fall within a sphere of the trusted distance to that presented query. While it's a very straightforward formulation, the problem is with complexity. Suppose you have 1 million, say, images, and from these images, each of them you have on the average 1,000 SIF descriptors. So you'll end up with a database of 1 billion, and you have to go over all these the vectors in a floating point procedure, and it's basically most of the times it becomes really the bottleneck of processing. So of course approximative solutions are to be considered and preferred, and we end up with a framework called approximate nearest neighbor search, which is not to be mistaken with artificial neural networks. What's happening in the state of the art for ANN? So a couple of methods are based on quantization, where there is you come up with a code book, and then basically for each item you extract indices or say codes from that, and these codes will refer to atoms in that the code book or dictionary. And then if a query is presented, you basically you go reconstruct these items from that learned code book. While they do a great job for compacting the database in terms of memory issues, They still don't do very much for complexity. Well, depending on this, how this lookup table is implemented, it could be, of course, it gives speed ups, but still within the same order. And another issue is that they have to provide also the code book. So you're basically given the code book and the codes, the indices, you can reconstruct, and there will be the privacy issues. A second family of methods are, I call them grouping methods. They are basically searching representative items in that original space of RD. And if a query is presented, it basically goes first, it matches with those items, those representatives or memory vectors, say, and then for a selected set of memory vectors, it goes inside and searches. So the great thing is that it basically makes the search non-exhaustive, which is great, but still in terms of memory, you even add to memory because you also have to have those the representatives again in the memory. And a third family of methods which are based on projections, which is probably the most famous. So you have a projector matrix, whether it's random projections or you learn it from the data, and the projected values are binarized, and you come up with short fingerprints or hash values. So basically the most research in this community is focused towards designing this projector matrix that we introduced later. No one is questioning this binarization part. You always think of hashes as binary values. But we asked this question, can we do any better? And it turns out that by ternarizing, instead of binarizing the projected values, we could do so. So let's see what's happening in a projection scenario. Suppose we restrict to random projections. Say we have a random projection matrix W that takes these random vectors F to represent the items in the database, and Q the query, and you come up with X's and Y's. And you know that there exists theoretical guarantees using random projections. You will basically preserve the distances from the original space in that new space of X and Y to some extent. So whatever the projector matrix is, we could think of its joint distribution between these projected values, X and Y. Either the data is originally Gaussian, or after this projection, due to the central limit theorem, they become somehow Gaussian form. So we end up with this, suppose this is one contour of the joint probability distribution, and we end up with this elliptical shape. Of course, the more noisy the values are, the less elongated this ellipse will be and more spherical it becomes. So then you binarize it, these values, you come up with a bunch of plus ones and minus ones, and then basically you come up with this binary hashing framework that you have your hash, after extracting the hash, you go and match it with the database, this time with Hamming distance instead of the original Euclidean distance. So the great advantage is that you come up with probably short binary codes which easily fit into memory. Even 1 million items could fit into the memory. And they are great because they are privacy preserving. You cannot easily reconstruct, given the hash values, you cannot really reconstruct the original vectors. And also you're avoiding basically the floating point operations. You come up with fixed points, binaries. But the disadvantage is that it's O of capital N. And you basically, you have to go again through all those 1 billion values. And also the performance is not great due to this bit flippings. You see that this is the ellipsoid of the joint distribution. You have these big regions which correspond to changes of flippings of +1 to -1. So the idea we propose is that let's put a reliability measure for these projected values, and we say that not all projections are as important as each other. Let's put these lambda x and lambda y here to basically think of this region as a void region. You don't do anything with that. And this region as robust, these regions as robust. These regions are what happens for your bit flippings, which is much reduced, but the other regions are basically robust hash values. And of course, we can compare them together and come up with this curve that for different SNRs, we have this probability of bit flippings reduced. Another argument can be from a signal approximation viewpoint, where you're probably familiar with this famous formulation that you're given your projector matrix and you want to find these codes which are as close as possible to those projected values, but you want some particular regularizations on top of them. You want probably that they be sparse, so you L0 regularize them. And the great thing is that here you have this closed form solution, which is basically under this L0, under L1 it's something else. That is basically this hard thresholding function that you only keep values which are more than or less than a certain value, certain threshold. But then what we can do for search, of course we need to come up with something which is not a floating point but fixed point. So here we can see that this idea of ternarization is much closer to this optimal solution of hard thresholding than binary encoding. So the whole setup will be like this, that it turns out that random projections for many cases is not enough, so we need to basically have a kind of decorrelating transform, be it DCT, or you learn it from the data, PCA, or even basically local PCA, whatever it is. You finally you decorrelate your data and then you apply random projections on top of it, and then you do this sparse approximation formulation and you come up with these +1s, -1s, and zeros, and you put those basically those data +1s and -1s in a lookup table, and then you go search. So basically the whole scenario can be summarized like this, that you have +1s, zeros, and -1s from the database side, and the query will be, this is basically a noisy ternary channel that your query will flip or not, and we can achieve a sublinear search performance, search complexity, by only considering +1s and +1s going to +1s, or +1s going to -1s, or vice versa, and doing nothing for these zero values. So for example, here we have, this is how we construct the lookup table, that we say, for example, for the first projector value, we have how many +1s, we put them to a database, to a lookup table like this, also for a -1 values, and then if a query comes, we do this algorithm, which is simply given 1 +1, matching 1 +1 from there, we basically kind of increase the probability that it is belonging to that item by this new value, and if it's a +1 going to a -1, we penalize it with this new prime. Yeah, and then in the end you come up with a long vector for all items, which is quite sparse, and then you pick the k-toughest values as your candidates. Some experiments, first of all, with synthetic data. Suppose we have a synthetic Gaussian setup that we for different values of SNR, different values of noise in the database, we say let's fix the probability of detection to this range, and for different complexity ratios we sketch these plots. So complexity ratio here for us would be first of random projections and then second of lookup table read. And for basically for the binary approaches like SIMHASH, it will be of basically just the original dimension capital D going to smaller dimension n, small n. And also for memory vectors, they also have their own definition, and we see that we get this kind of orders of magnitude performance change. And also we can think of how compact they are. We see that especially for this region, they are even more compact, and this compactness is characterized by the entropy of those codes. So we have another example from image retrieval, that this database of 1 million items, Flickr plus Holiday, and also another database, UKB, they are basically of image retrieval. And again, we get this performance gain over the other methods. And this is again the definition of complexity ratio that we achieve, which this final term is basically going to pick from to further refine the list of this L size. And also a last experiment of PUFs, or physical unclonable functions, a database of packages, consumer packages, which we also compare, and we get this complexity advantage. So to sum up, we were talking about the problem of fast search, and we saw that what literature proposes is projection plus binarization. What we propose simply is to ternarize those values. And we saw that by introduction of those thresholds, the bit flipping probabilities will be reduced. And what we didn't present in this paper is that we define a concept of coding gain, which is basically the amount of mutual information that is preserved between the original values and the coded values, and divided by the entropy, which is a measure of compactness of the codes. And we don't show it here, but in another work we show that we always get this advantage. And we also get more flexibility of design, because we could also increase the dimensions and still make it bounded by very high values of threshold. So you could get a very small entropy, but with a very long block length. And you have to be, the downside is you have to be careful about the design of these lambda x and lambda y. Either you have a model-based approach that you could exactly see what those optimal values are, or you basically do it with cross-validation. You come up with your lambda x's and lambda y's. So that's it. Thank you very much. And
so thank you to your speaker. Do you have any questions? I have a question.
Sure.
Okay. About approximate nearest neighbor search, as you say, there's a lot of literature, and you consider the as basic comparison locality sensitive hashing, which is just the basic one. But there are many other approaches, like, for example, iterative quantization, inverted multi-index, and so on. There is a specific reason you did not include in your comparison?
It's basically, our point is that we don't want to talk about the projector, because what literature does is, for example, every ICML, every NIPS has 2 or 3 papers about this, that they come up with all sorts of formulations or even deep neural networks to design the projector matrix, and then they binarize.
Yes, okay, I understand. And also understand that the most important thing is to consider the accuracy with respect to the speed of the algorithm, while not all of these techniques do, but some actually are very good and has performance that are very much better than the basic one. Okay, we can talk later about this.
Sure. Yeah, but anyway, the point was to make this complexity ratio clear. We can define this complexity ratio.
Okay. And have you also not considered the work by Karian about sparse approximate nearest neighbor search?
Sparse approximate?
Yeah.
Probably
Okay.
2015.
We can talk. We can talk
sure.
about this.
Yeah.
Okay. Thanks
Thank
again.
you very much.
Okay. You last.
Okay, so this is the end, as Taha said. Thank you very much. I hope you had a great event, and I hope you enjoyed Abu Dhabi. For many of you, it was the first visit here, I understand, and I hope you come back again. A couple of opportunities will be, there is a winter school in biometrics that we've been flashing on the screen in January, and it's only for $750, which includes room and board. So you get a place to stay, and you get food all day, and you get to learn from the top security professionals in the world about security and privacy of biometrics. So I encourage you to apply to that. And also we'll have Asia CCS, a leading security conference in the region that'll be held here in March. And so that might be another opportunity for you to visit Abu Dhabi again. And finally, the Center for Cybersecurity that sponsored this event is hiring. We're looking for postdocs, faculty, visiting professors, all kinds of opportunities. So feel free to send in your applications. Thank you.